Welcome to this MOOCs online video course Theory of Yarn Structure. Today we will start module 5. Module 5 discusses about mass irregularity of yarns. Any longitudinal fibrous assembly like slaver, roving, yarn, they are produced by certain technological processes. Therefore, it is evident that those technological processes will impart certain natural irregularity in the yarn or in the slaver or in the roving. This irregularity is natural. So, what are the reasons of this irregularity, or how do we discuss about this irregularity? This irregularity can be associated with any attribute of the assemblies. For example, this irregularity can be related to mass, or this irregularity can be related to diameter, or this irregularity can be related to volume, or this irregularity can be related to packing density. That means, let us take slaver. If we divide the slaver into some equal parts, then we measure the mass of those parts, we will see that the masses will be different. The same situation will happen in case of volume of slaver or packing density of slaver, diameter of slaver, like that. So, irregularity can be associated with any attribute of the material. In this particular module, we will focus on mass irregularity. That means, the mass or the weight of slavers at different positions along the slaver is different, and we will talk about the natural causes of irregularity. So, for example, irregularity can be generated by also say poor fiber material, or it can be generated due to some faults in the machines. They are preventable irregularity. So, we will not discuss them in this module. However, we will talk about the natural mass irregularity in yarn. Probably the first theoretical concept about mass irregularity of slaver or yarn was introduced by Martindale in the year of 1945. So, Martindale tried to analyze the mass irregularity of slaver, and Martindale's model is also applicable to yarns. Martindale thought about a slaver which is prepared of fibers. Then he introduced certain basic assumptions. First assumption, what he thought is, all fibers have same length. This was his first assumption. Second assumption, fibers are straight and parallel to the axis of the sliver. Third assumption was fibers are deposited individually to form the sliver. What does this mean? You have seen a drafting system. So, the third assumption indicates that the fibers move individually in the drafting system to form a sliver. That means, no two fibers are together or no three fibers are together. That means, fibers move individually or they are deposited individually to form the sliver. So, these three were Martindale's basic assumptions. Apart from that, he also introduced one important assumption that we will discuss later on. Before that, we would like to see how he imagined about the formation of sliver. So, this picture depicts the formation of sliver according to Martindale's model. What you see in this diagram is there is a length capital L. We will consider this as sliver length. In this length capital L, there are many fibers present. These are the fibers. Each fiber has length small l. All fibers have same length. So, all fibers have length equal, that is small l. The downward arrow indicates the deposition of sliver. So, here imaginatively slivers will fall at the bottom and they will form the sliver. We consider a small point A. On this point we draw a line, dash line. What is the probability that a fiber is passing this line at A? Now, if a fiber is passing this line at A, that means the right end small circle of the fiber must be lying within a length small l. If a fiber is passing this line, that means the right end must lie within small l. otherwise they will not be passing this line. Say for example, this fiber is passing, so its right end is lying within this L, this fiber is passing, so its right end small circle is lying within this length, right. This fiber is passing, so its right end is lying in this length small l, this fiber is passing, so its right end is lying within this small length L, and what is the total length? Total length is capital L, that is the sliver length. So, this probability, the probability that a fiber is passing this line refers to the so called geometric probability. This probability must be equal to small l by capital L. So, what is the probability that a fiber is passing the line at A? This probability is equal to small l by capital L, because the right end, if a fiber is passing this line, then its right end must lie within a small length L, and what is the total length possible is capital L. So, small l by capital L is the probability, right. Now, suppose total number of fibers in this sliver is equal to capital N, right. So, number of fibers per unit length of sliver is equal to say small n 1, that is equal to capital N by capital L, right. Then the probability that small n, this small n is much less than capital N fibers passing the line at A follows binomial distribution. This binomial distribution, the probability of this is capital N C n, probability to the power n, failure to the power capital N minus n, right. This binomial distribution has certain parameters, for example, mean value, small n bar is capital N into P, right. Variance is n into P 1 minus P. So, this is the variance of binomial distribution. Then coefficient of variation, is equal to square root of variance, that is standard deviation divided by mean. So, root over n p into 1 minus p by n p. So, root over 1 minus p by root over n p. Further, we can write root over 1 minus p by n p is your n bar, right. By the way, we often abbreviate coefficient of variation by C v. So, C v stands for coefficient of variation. You might have noticed that in this expression C v, coefficient of variation, is dimensionless. It can be expressed in percentage if we multiply this by 100, right. So, theoretically we deal with dimensionless C v. However, it is possible to deal with C v also in percentage. In that case, we have to multiply by 100. Okay. So, this is basically the coefficient of variation of number of fibers present in the cross section of sliver, right. Now, we will talk about coefficient of variation of mass irregularity. There are small n number of fibers present. We denote each fiber by a subscript I, where I will be equal to till n. Similarly, fiber fineness we will denote by T 1, fiber number 1, T 2 is the fineness of fiber number 2. Similarly, T n is the fineness of fiber number n. Coefficient of variation of fiber fineness we denote by V t. Again it is dimensionless. Now, we will consider a very short length in a sliver. Say we come back to our sliver formation diagram. Here you see a small length dx. So, what is the mass of sliver in this small length dx? So, the mass will be obviously very small because the length is very small. So, let us denote this small mass by dm. So, what will be the mass of sliver of this small length dx? So, the mass dm can be 0 if there is no fiber when n is equal to 0. Otherwise, this dm can be mass will be summation of all fiber mass. So, what is all fiber mass? That is fiber fineness into length, mass per unit length into length, and this summation I is equal to 1 to I is equal to n, when n is equal to 1 to like that. So, this is the mass of sliver element. Small element of sliver, right. Now, what will be local sliver fineness? Local sliver fineness means fineness of a small element of sliver. T, this is mass by length, dx is the length and dm is the mass. It can be 0 when n is equal to 0. Fineness is 0, which is little odd to hear. That is why we use the word local. If we choose a very small element of a sliver, there can be no fiber. So, in that very small element, fineness can be 0. That is why we use the word local sliver fineness. Otherwise, this T is equal to dm by dx. What is dm? dm is your Ti into dx by dx, that is equal to summation Ti, because dx is constant, and the summation will vary from I is equal to 1 to I is equal to n, when n is equal to 1 to like that. Right. Now, so what we see is that sliver fineness can be 0 if there is no fiber, but if there is a fiber, then sliver fineness is equal to summation of fiber fineness. Now, fineness of sliver is different at different positions along this sliver, because the number of fibers will vary in the cross section. Some parts number of fibers cannot be equal to the number of fibers in other parts because of the technological operations. So, sliver fineness capital T is a random variable, right, and how this is related? This is related with T can be 0 when n is equal to 0, else T will be summation Ti 1 to n when n is equal to 1, 2 and others. Now, we have to find out the coefficient of variation of sliver fineness, that is V of capital T. What is the expression of coefficient of variation of sliver fineness when these two equations are valid? Now, we will now go back to mathematical statistics and review the part of mean, variance, standard deviation, all those things. So, So, if you take any standard handbook on mathematical statistics, you will see this part. Suppose y is a random variable which is equal to 0 for m is equal to 0, or y is equal to summation of x I is equal to 1 to m for m is equal to 1, 2 and others. Here m is a discrete random variable, is a number. Whose mean we denote by expectation of m. E stands for an operator of expectation, and variance we denote by dm. D stands for the operator for variance, and we know variance is related by this. So, this is the definition for variance. Okay. Then what we think is that each x I is a random variable with common mean and common variance. If we consider this, then mean expectation of x I becomes common. Similarly, variance of x I becomes common. Similarly, coefficient of variation of x I becomes common. So, this is your mean, this is your variance, and this is your CV, coefficient of variation, right. Then we can write variance of y. What is y? Y is 0 when m is equal to 0, y is summation x I when m is 1, 2 and this. If such is the definition of a random variable, then its variance of y can be written as follows: expectation of m, variance of x, CV of square of CV of square of variance, CV of x plus variance of m by expectation of m. This derivation you will see in a standard handbook of mathematical statistics. So, if this is how we define y, then the square of CV of y is 1 divided by expectation of m into square of CV of x random variable plus variance of m divided by expectation of m. Now, we compare this with our expression of fineness 0 when n is equal to 0 and capital T is equal to T I when I is 1 to n is equal to 1, 2 and dot, right. Then variance square of C v of this is equal to 1 divided by expectation of n. Expectation of n is mean of n. So, n bar into square of C v of fiber fineness plus variance of n divided by expectation of n. Right. We will now work with this expression. So, the square of C v of sliver fineness is equal to 1 by n bar v square t plus sigma a square by n bar. Okay. We substitute variance and mean from binomial distribution. What was variance? This was the variance, and what was the mean? N into P. So, if we substitute, what we get is so, if we assume that the number of fibers in the cross section of sliver follows binomial distribution, then the square of C v of sliver fineness can be expressed by this form. Right. Okay. So, in order to find out square of C v of sliver fineness, you need to know mean number of fibers present in the cross section of sliver. You need to know the square of C v of fiber fineness, and most importantly you need to know the probability P. What is this probability? This probability is small l by capital L, which is often difficult to find it out. So, we introduce now an alternate assumption. What is that? That is number of fibers in the cross section of sliver follows Poisson distribution. number of fibers in the cross section of fiber follows Poisson distribution. This infers L limits to infinity. So, n total number of fibers also limits to infinity. When L limits to infinity, the probability tends to 0. So, under the assumption of Poissonian distribution, the probability becomes 0. Then we can write in this expression, if we substitute p is equal to 0, then we can write v square t is equal to 1 by n bar v square t plus 1. Then V t is the CV of sliver fineness root over 1 by n bar V square t plus 1 this. And what is n bar? All fibers are parallel, they are straight. So, n bar is capital T bar by small t bar, mean sliver fineness divided by mean fiber fineness. If we substitute here, then we obtain small t bar by capital T bar V square t plus 1. So, this is the most important equation till now. So, this expression is developed based on 4 assumptions. First assumption, all fibers have same length. Second assumption, fibers are straight and parallel to sliver axis. Third, fibers are deposited individually and of course randomly, then only the statistical distribution comes into picture. To form the sliver, you remember these 3 were the basic assumptions of Martinez model, and the fourth assumption, number of fibers in sliver cross section follows Poisson distribution. So, this expression is true under these 4 assumptions. Now, often in textile books, research articles, this V t is known as limit irregularity, and it is expressed as follows: C V limit is equal to T bar by this into V square T plus 1. So, C V limit stands for limit irregularity. So, this is the expression for limit irregularity. Right. Suppose V t is equal to 0. What does that mean? Fibers are uniform, their fineness at different positions along a fiber are same. So, there is no irregularity on fiber fineness. So, the C V of fiber fineness is 0. If we substitute V t is equal to 0 here, then what we will find? C V limit will be this. This expression also you will see in many books. So, in this case one more assumption is considered, that is V t is equal to 0. So, often it is said that this expression is true for sliver prepared from synthetic fiber. And suppose V t is equal to 0.3516. So, that is basically 35.16 percentage. So, if you substitute this value here, then you will find C V limit is equal to 1.06 by this. Often said, this is the limit irregularity of sliver prepared from cotton fibers. By the way, if we express in terms of percentage, then this is dimensionless. So, these expressions are quite well known in traditional textile literature, and this is how these expressions are obtained. So, if we summarize Martindale's model, Martindale's model is based on 4 important assumptions. The basic assumptions are: sliver is prepared from fibers, all fibers have same length, all fibers are straight and they are parallel to sliver axis. The fibers are deposited individually and randomly to form the sliver, and the special assumption is the number of fibers in the cross section of the sliver follows Poisson distribution. Under these 4 assumptions, it is possible to derive this expression for limit irregularity. It is a quite general expression. If you know the CV of fiber fineness and you know the mean number of fibers present in the cross section of the sliver, you will be able to calculate limit irregularity for that sliver. 2 special cases we considered. If we consider there is no irregularity of fiber fineness, then this limit irregularity becomes this. This is often it is said that this expression is true for the sliver prepared from synthetic fibers. If we consider cotton fiber fineness CV is equal to 35.16%, then you will obtain CV limit is equal to 106 root over n bar. Often said this expression is valid for the sliver prepared from cotton fibers. So, this was Martindale's model. Now, we would like to discuss a very interesting problem. The problem is the relation between CV of fiber fineness and CV of fiber diameter. This problem comes from typically wool fiber. The size of wool fiber is often expressed by their diameter in the unit of micrometer. If we know the CV of fiber diameter, is it possible to know CV of fiber fineness, so that we can use Martindale's equation to find out the mass irregularity of the sliver prepared from such fibers. So, this is the origin of this problem. What is the relation between CV of fiber fineness and CV of fiber diameter? Now, if we go back to our module 1, where we discussed about basic fiber characteristics, in that module we derived a relation of fiber diameter, where D stands for fiber diameter, T stands for fiber fineness, rho stands for fiber density, right. Then we can write fiber fineness is equal to pi times rho by 4 into d square. For a given fiber, rho is constant and obviously pi 4 they are also constants. So, this becomes a constant. Suppose we write this constant by k, then we write k d square, where k is a constant. Right. Then we differentiate t with respect of d, then we obtain 2 k d. Okay. Now, we need to find out an expression for fiber fineness around mean value d bar. That means, fiber fineness around mean value d bar. This can be obtained using Taylor series. What does this Taylor series say? This T is equal to k times d bar square plus first derivative at d bar divided by factorial 1 into d minus d bar plus other terms. So, what do we obtain? K times this plus 2 k d d bar minus 2 k d bar squared, that is equal to 2 k d d bar minus k d bar square, right. Approximately we can write, taking the first two terms of Taylor series, what will be the mean and variance of T? Mean of T is equal to expectation of T, that is equal to expectation of 2 k d d bar minus k d bar square. K is a constant and d bar is also constant. So, we can write 2 k d bar into expectation of d minus k d bar, then we can write 2 k d bar, expectation of d is d bar minus k d bar squared. So, 2 k d bar squared minus k d bar squared is equal to k d bar squared. So, this is the expression for mean fiber fineness, and what will be the expression for variance? Variance is sigma t square, right. So, what is this sigma t square? Sigma t square is expectation of t minus mean of t. So, this is the definition of variance. We often write, so this we substitute, what is your t? T is your 2 k d d bar minus k d bar squared minus mean of t. What was mean of t? K d bar square. So, what we obtained? Expectation of 2 k d d bar minus 2 k d bar square. So, here 2 k d bar is constant. So, 2 k d bar into expectation of d minus d bar square. So, 2 k d bar square, expectation of d in d bar square, that is sigma d square. Okay. Then coefficient of variation of t is sigma t by t bar. What is sigma t? Sigma t is 2 k d bar into sigma d by what was t bar? T bar was k d bar square. So, 2 sigma d by d bar. What is sigma d by d bar? Standard deviation of d divided by mean of d. So, 2 v d. This is C v of d. So, V t is equal to 2 into V d. This is another important relation. So, if we substitute these two Martindale's expression V t t bar by t bar V square t plus 1. So, t bar by capital T bar, V square t is 4 V square d plus 1, right. In terms of unit, C v limit equal to 100 into 1 plus 0.004 C v square d in terms of percentage divided by root over n bar 0.0004, right. This expression also you will see in many standard textbooks. We will stop here now. In the next discussion, we will talk about very interesting fact, when the fibers are inclined, then what will be the irregularity and also the doubling. Thank you for your attention.